3.7 Rates of change in the position function. Essential question: can I describe the motion of a particle using position, velocity, acceleration, and speed? The three important concepts of motion. These are the important vocabulary when we talk about motion: initial, origin, rest. Velocity is positive, we're moving to the right. Velocity is negative, we're moving to the left. Down here, when acceleration is negative, the velocity is decreasing. In order for a particle to change the direction, velocity must change signs. Let's take a look at a problem where we look at position. This kind of motion that we're discussing is just motion along a line. All right, so x of t represents the position on the x-axis, and time is at what time it occurs. We're going to look at velocity and figure out when it is at rest. So we find the velocity, set it equal to 0, and find the times when it is at rest, -1 and 3. -1 is not a time we're going to be using in our experiment, but we do want to look at the interval from 0 to 3. These values, when you put it into the velocity function, will yield a negative value. When you put values like this into the product right here, we will get positive values. So this tells us we're moving to the left and then moving to the right. So here on our position line, we're starting at 4. At t equal to 0, we know we're at 4, t equal to 0. And this says we're going to move to the left, and then we're going to move to the right. Let's go ahead and figure out what these positions are. S sub 3 will be equal to -5. So if I put -5 into this function here, I will get -5. Now if I figure out what S of 6 is, x of 6 is going to be 22. So over here we're going to have 22. Now the mistake most students make is to find total distance. They just do S of 6 take away S of 0. Now when you do that, you're going to just take 22, take away 4, and you're going to get 18. You're just finding the displacement. To figure out total distance, we must take into account all the distance that's traveled. So the distance traveled from here to here is 9, and distance, remember, is positive, and the distance from here to here, that's going to be 29. So the total distance traveled is 38. It's a big difference from displacement to total distance traveled. All right, here's an example, a numerical example where we look at velocity. So here's a table of time and velocity. At time t equal to 0, is the particle moving to the left or to the right? Okay, at time equal to 0, the answer that is that it's moving to the left because velocity is negative. Is there a time on the interval when the particle is at rest? And the answer is yes. How do I know that? Because I had a velocity that's negative, and then I have a velocity that's positive, so sometime it must have become 0. So because the function is differentiable, and then it is continuous. So that means we need to have all the values from -3 to 2 included in there. And by the mean value theorem, there is a velocity equal to 0. From the table, can we approximate v prime of 10, which is acceleration? Acceleration of 10, which is velocity at 10, and we can approximate it, that's about the best we can do, by doing the velocity at 12 minus the velocity at 8. These are the two values that are closest to 10, divided by 12 minus 8. And so that'll be 5, take away 7, all over 12 minus 8, which is -2/4, or -1/2, and this is meters per minute squared. This is velocity. A of t denotes the acceleration. Is there guaranteed to be a time equal to 0 to c in the interval where the acceleration is equal to 0? I'm going to look at this spot and this spot. And the reason I'm looking at that is because I know that the average rate of change of velocity. So v of 12 take away v of 6, all divided by 12 minus 6 is equal to 5 take away 5 all over 6, which is 0. This is the average rate of change, and because it's differentiable, I know that the mean value theorem is going to be able to be applied, so that there's going to be some instantaneous rate of change at C, which we could call A of C, in which it's equal to the average rate of change. So the answer is yes by the mean value theorem. All right, let's take a look at using velocity in a graphical sense. If t is equal to 4, right here, is the particle moving to the right or to the left? And it's moving to the right because velocity is positive. Over what time interval is the particle moving to the left? And this is when the velocity is negative. So I'm going to say 5 less than t less than 9 because velocity is negative. At t equal to 4, is the acceleration of the particle positive or negative? At t equal to 4, we're looking at acceleration, which is the velocity, is the derivative of velocity. It looks like it's going to be negative. So negative because the velocity is decreasing. What is the average acceleration of the particle between 2 and 4? So I'm going to do acceleration average, which is the velocity at 4, take away the velocity at 2, all over 4 minus 2, and this ends up being negative 3/2, and we are in feet per second squared. All right, now, is there a guarantee, so this is between 2 and 4, is there a time in which the instantaneous rate of change is equal to the average rate of change? So this is the instantaneous rate of change, this is the average rate of change. Is there a time period here? So the question is the mean value theorem appropriate here? And the answer is no. And why is it? Well, it is continuous, but it's not differentiable, and it's not differentiable because of that corner right there. All right, you try this problem. Stop the screencast and see if you can answer all those questions. And here's the answer. Now let's discuss the relationship among velocity, speed, and acceleration. What effect does an absolute number have? It means that anything you put in, you'll always get a positive out. What effect does the absolute value have on a function on its graph? And let's go ahead and take a look at that. All the output has to be positive. So here's a function. Let's say y equal to f of t. Now, the absolute value would look something like this, where all values that were negative are now positive. So we have a partial reflection going on there. Okay, let's go ahead and study. There's 4 situations. After the 4 situations, hopefully you can make a conclusion. Here's a velocity graph. Here's the velocities, and the speed is always the absolute value of velocity. So this is 1, 2, 4, 8, and 16. Now in this case, the velocity is above the x-axis, so it's positive, and the velocity is also getting larger, so it's increasing. Because the velocity is increasing, we know the acceleration, these values right here, is going to be positive. All right, so by examining the graph of speed in the table of values, we can conclude that speed is, and you can see the numbers are getting larger, it's increasing. So the highlighted part, look at velocity, look at acceleration. After situation 4, hopefully you'll see a pattern. Okay, try this one on your own, and I will show you the answers. And here are the answers. Again, notice velocity is negative and acceleration is negative, and the conclusion is that speed is increasing. Okay, try it again. Stop the screencast and fill out this. The answer is that when velocity is negative and acceleration is positive, that speed is decreasing. Try it again. This is the last situation. Fill it out. Stop the screencast. And here's the answer. Velocity is positive above the x-axis. Acceleration, the derivative of velocity, is negative. And notice that speed is decreasing. So in which situations was the speed increasing? That happened when velocity is positive and acceleration is positive, or velocity is negative and acceleration is negative. So when they have the same sign, we notice speed is increasing. When is the speed decreasing? Velocity is negative, acceleration is positive, or velocity is positive and acceleration is negative. We notice that the speed was decreasing when they have opposite signs. Here's a little test. Let's see if you can finish it, stop the screencast, and do it. And here are the answers. This is an example from Stewart. These are the kinds of questions that you need to be able to answer. And here are the answers. You need to be able to recognize that velocity is the first derivative of position, and that you should be able to evaluate a velocity at a certain time. You should be able to find the particle at rest by examining the velocity curve. You should also be able to decide what direction a particle is moving by looking at the velocity. And remember the little hint that I gave you. Looking at a sign chart of velocity is very useful, especially when you put in the times at which the particle's at rest, and then you examine within those time intervals whether it's positive or negative. Once you do that, then you find the positions at all of these times, beginning, end, and all the times of rest, and then add up the totals. Finding acceleration is the derivative of velocity, and looking at all the graphs and deciding when speed is increasing or whether it speeds up or slows down according to how you examine velocity and acceleration at the same time period.